Hi everyone, welcome back to another video of Ethereum Basics. In this video, we'll discuss nodes and clients in detail. So by now, you already know that Ethereum is a distributed network of computers running a software that can verify the blocks and transaction data. These computers are known as nodes or network operators, and they are any instant of Ethereum client software that is connected to other nodes also running Ethereum client software. And these peer to peer connected nodes form an Ethereum network. This client, that is Ethereum client software, is an implementation of Ethereum that verifies the data against the protocol rules and keeps the network secure. So the client is basically a software, a programmatic implementation of the Ethereum specification that could be written in either Go, Java, Rust, Python, or in any other language. Irrespective of the language the client is written in, it would work and behave in the same way as per the Ethereum's technical specification. It doesn't matter what kind of client the node is running, the functionality exhibited by the node would be the same. Now, coming to node architecture, an Ethereum node has to run two clients. One is an execution client, and the other is a consensus client. The execution client is responsible for transaction handling, transaction gossip, state management, and supporting the EVM, that is Ethereum Virtual Machine. On the other hand, the consensus client is responsible for building blocks, gossiping them in the network, handling the consensus logic, whatever consensus mechanism the network is following, and managing fork choice in case of conflicting blocks. So, in the diagram here, you can see that the entire Ethereum network is actually a peer to peer network of multiple nodes, each running a consensus and an execution client. The communication happens between the consensus client and the execution client within a single node and among all of the nodes as well. There's another client called the validator client, which comes bundled with the consensus client and can be added to the node at any time. So, if the node wants to participate in the process of proposing the blocks and adding them to the blockchain, they can add the validator client to their consensus clients by depositing a stake of 32 ETH in the deposit contract, and that would make the node eligible to propose new block. The validator handles the attestations and the block proposals, and they also enable a node to accrue rewards for producing block. If you recall, in one of our previous videos, we mentioned that there's a static block reward for producing a block and adding it to the network. So adding this validator client helps the node in producing the block and earning block rewards in exchange for it. This also makes the node liable for any dishonest activity, and if they are caught doing any kind of malicious activity on the network, a penalty is levied and their collateral, that is the 32 ETH, can be slashed. So to summarize the clients, we have execution client, which gossips transactions over its P2P network. It executes and re-executes transaction. If you remember, anytime a transaction is added to a block, the block is propagated to the network and the other nodes of the network re-execute all of the transactions to verify and validate them. Execution client also verifies incoming state changes, and it manages the state and receipt trees. State and receipt trees is a concept that I haven't covered yet. There are basically three trees in Ethereum: storage, state, and receipt. So, storage we have already covered in accounts. And these two are similar to it in the sense that it contains some additional data about the network. We'll cover these two in detail in our Ethereum advanced part. So, coming back, execution client also creates an execution payload, and it exposes a JSON RPC API for interacting with Ethereum. So whenever you are interacting with Ethereum using Web3.js or any kind of node as a service, you are basically fetching the data from execution client. Then we have the consensus client. Consensus client gossips blocks and attestations over its P2P network. It runs the fork choice algorithm in case of conflicting blocks, and it keeps the track of the head of the chain. Consensus client also manages the beacon state, and it keeps track of accumulated randomness in RANDAO. RANDAO is basically an algorithm that decides which user would be picked to create, produce, and add blocks to the network. And it also keeps track of justification and finalization of the blocks. Lastly, the validator client proposes blocks, accrues rewards and penalties, it makes attestations, it requires 32 ETH to be staked in order to be activated, and it can be slashed. Now we already know that these clients are basically softwares written in different languages. So different teams are working on different clients. There are Git, Open Ethereum, Aragon, Nethermind, Besu, Teth, CoreGit as execution clients, and Prism, Lighthouse, Teku, Nimbus, etc. as consensus clients. So it is very important that we have appropriate client diversity in the network, because if any one of these clients has a major share, for example, you can see that Get here has 83% share. If there's any bug in the Get client, you can say that 83% of the network is compromised. Having client diversity also makes the network resilient to attack, because one client would be written in one programming language, the other client would be written in another programming language, and we all know that each programming language has a flaw of its own. So, if we have appropriate client diversity, a flaw of one language, which would be exhibited by one client, wouldn't be replicated in another client which is written in different programming language. For example, one is written in Python and the other is written in Go. So, the flaws that the first client will have because of being written in Python won't be there in the second client, which is written in Go. This is different from the first point because bugs are something that you can say are a logical error in writing the implementation of Ethereum specification, while the fundamental flaw of the programming language is a different thing altogether. For example, there are two different clients written in Go, and there could be a bug in one client only because that team missed out on something. While if there's a problem with the Go language itself, both of the clients are at risk. That's why we need diversity in terms of programming language as well as the client implementation on top of it by different teams. Client diversity is also important for POS finality because if one client has a majority share, it creates an attack vector in the sense that it could be hacked and it could be used to create a new chain altogether that would become a main chain, and that would be a compromise chain as well. For example, here Prism has 66% share, and if this client is hacked, you don't know when a new block is proposed, it already has 66% majority. So, if this client is hacked, a malicious actor could compromise the entire chain and it can fork it and make that the main chain. There's also an aspect of shared responsibility. If one client is being used more than the others, then the accountability of keeping up the integrity of the entire network comes down to a very small group of individuals, a very small team. So that is also not good for the ecosystem. Now, coming to the node types, there are three different types of node that consume the blockchain data differently. These are full nodes, archival nodes, and light nodes or light clients. So, full nodes do a block by block validation of the blockchain, including downloading and verifying the block body and state data for each block. Regardless of from where the verification starts, some of the full nodes start from the Genesis block and they then verify every single block in the entire history of the blockchain, while some other nodes can start from any block in between that they trust to be a valid block. Irrespective of from where the verification starts, from the genesis or from midway, the full nodes only keep a local copy of the relatively recent data. It's generally 128 blocks. Archival nodes or archive nodes, on the other hand, are similar to full nodes. There's just one small difference that they never delete any of the data. The full node only keep the relatively recent data, like past 128 blocks, but archival node keep all of the data starting from the genesis. So these nodes basically build an archive of historical states, and this data can range in terabytes and petabytes. This data is usually handy for services that heavily rely on blockchain data like block explorers, wallet vendors, and chain analytics organizations. In the last, we have light nodes. Instead of downloading every block, light nodes only download the block headers. These headers contain summary information about the contents of the block, and if the light node requires any other information about the block, they request it from a full node. They can then independently verify the data that they receive against the state roots of each block header. The main advantage of light nodes is that they enable users to participate in the network even if they don't have the necessary resources to be able to run a full node. There's one other type of node called boot node. Whenever a new node joins the Ethereum network, it needs to connect to nodes that are already on the network in order to discover new peers. These entry points are called boot nodes. A list of boot nodes is already hard coded into the client, and these boot nodes are typically run by the Ethereum Foundation's DevOps team or the client's team themselves. There's also another thing called node as a service. So, running your own Ethereum node can be very challenging. You have to accumulate all of the resources, you have to get to the required hardware requirements and the bandwidth requirements, and setting up a node, running it, maintaining it could be very challenging, especially when you are new to the network or if you want to scale really fast. So there are a number of services that already run optimized node infrastructures for you, so you can actually focus on developing your applications instead of worrying about how do you go about setting up a node and managing it. These node service providers run distributed node clients behind the scenes for you, so you don't have to. These services typically provide an API key which you can use to read and write from the blockchain, and they often provide supports from the different networks of Ethereum like Mainnet, Gurley, Sepolia, or Holsky. Some of the example of these services are like Alchemy, Infura, etc. So that was all about nodes and clients, and in the next video we'll cover networks in detail.